Hello guys, how are you doing today? My name is Lalto Sugrim, and today our video is based on geospatial databases and PostgresSQL using PostGIS, with the objective of explaining geospatial databases using examples in a PostgresSQL database with the PostGIS extension, and we're going to further explain what spatial relationships, spatial joins are, and why are they so helpful. So this is going to be the agenda I have outlined here for you today. We're going to go right into it, looking in what are geospatial databases, what is this PostgreSQL, what is the PostGIS extension. We're going to do some examples on that, and then we're going to look at spatial relationships, spatial joins, understand why they're helpful, and look at some examples there as well, and then we will conclude. So let's get into it. So, geospatial databases are specialized databases that are designed to store, manage, query, and analyze data that is tied to some geographic location. Now, unlike conventional databases that work primarily with numeric and text data, geospatial databases support spatial data types. So, this will include things like your points, your lines, your polygons. And these systems use specialized indexing like R trees and spatial functions such as calculating distance, intersections, and even containments to make sense of the data that is tied to to that geographic location. And that means they are instrumental in fields like urban planning, environmental monitoring, for navigation, and much more because they allow us to ask questions like which areas, let's say, are within this certain distance of a river, of a street, of a road, of a bridge, of a house, of a building in general, or which city block, let's say, contains the most amenities, which one contains medical services, a hospital, a police station, a fire station, a fire hydrant, right? So it allows us to ask questions, and more importantly, it is able to answer those questions in most cases, providing the data is there. Now, what is the PostgreSQL? Now, PostgreSQL, and it's commonly just known as Postgres, is an advanced open source relational database system, right? And it is actually celebrated for its robustness, for its reliability, and for its extensibility, right? That is because Postgres supports a broad range of data types and complex queries. Out of the box, when you get it, Postgres, it is able to manage data with standard SQL, but it's also designed to be enriched with extensions that are able to handle specialized needs. In our case, geospatial data processing. And that is what actually brings us now to what is the PostGIS extension. So, first of all, the PostGIS is an open source extension for Postgres, all right? And it transforms that database into a full feature GIS. What is GIS? A full feature geographic information system, right? So it adds support for spatial data types, like obviously those that are geometrically based and those that are geographically based, right? And it hosts a whole array of spatial functions like contain, intersects, within, right? And I mean, there are endless geospatial functions like those that the PostGIS extension allows for us to perform directly in SQL in our database. That means we can run these queries to calculate areas, measure distances, perform spatial joins, and even possible to overlay spatial data, right? All within that Postgres database. So the ability to combine this standard relational queries with advanced spatial operations is what makes PostGIS a powerful tool for handling location-based data. Now, moving forward, how do we enable the PostGIS extension? So upon installing Upon installing the Postgres database, right, you will see the option there, spatial extensions, as you're seeing on the bottom right, and you must download and install the PostGIS bundle as well. Now, upon installing this bundle, you will then head into your database, which I am now going to do. Let me just head into it here. Let me just confirm you are seeing that screen. Yes, you are seeing. You head into Postgres admin, PG admin 4 here. You head to your servers, right? Servers are loading, right? You then select your database. In this case, I have four databases, and we are looking at New York City, NYC. Well, you're seeing here, I already have the PostGIS extension, but if you did not have it, after installing the bundle, you would then go to the query tool. It's loading good. And you would enter create extension PostGIS. Now, as I already have it, I will not do that again. But what you can do to confirm it's installed and it is running is by copying, whoops, my bad there, by copying that query there, and let's run it here. And you're seeing we're selecting the PostGIS full version in the database. Sorry, yeah, in the database, and you're seeing PostGIS 3.5.2, the extension is present here. So I know it is active on this database, right? Now, while we're in here, let's look and understand the database. So there are the extensions. So there's the PostGIS extension, the one, well, we would have just added. I would have added it a bit before. And this is where on the tables, oops, where did it go? Yeah, the tables here are your data, right? So New York Census, see New York Census blocks, it has a few columns. The GID, the population total, population of white, of black, of native, of Asian, of other, their borough names, right? So these tables represents the data, right? There is the New York streets, their name, which is one way, their type, their geometries, right? Right. And in this case, as I've said before, this database is representative of New York City. Good. So moving forward, all right, we are going to do some practical applications. Um, whereas we try and understand and I'm going to try and show you the possibilities of using the geospatial database, right, with a PostGIS extension. What are the possibilities? What are some of the things you can do? And truly, it is endless in some aspect, and it all depends on the data you have. So the first query we have here, right, is that it selects all the neighborhoods where the borough name is Manhattan. Right? So the key function here is select name. So it's going to retrieve all the neighborhood names where borough name is Manhattan. It's very simple once you understand the language to some extent. So it limits our selection here to Manhattan. So let's run it and see what we have. So as you're seeing here, in the borough of Manhattan, there are 28 28 neighborhoods present there. Now, what is the use case of this query? So, in real world scenario, it allows us to quickly list neighborhoods. Let's say for some geographical studies or for some demographic studies, rather than going on a map and clicking and seeing. Oh, sorry, not clicking. Looking and seeing what encompasses this borough, right? Moving on, we're also able to calculate total population, right? So what we're seeing here, we're using the census blocks in New York City, and then what are we doing? We're summing the population n underscore total fields. All right. And in that sense, we're aggregating the total population from the New York census blocks. All right. And a use case for these types or this type of operation, this type of query, is that it allows us to do demographical studies or analysis and reporting, on a in a more not comprehensive, sorry, on a more efficient scale. All right. So we're seeing here in New York City, the total population is 8,175,000 and 32 individuals. I believe the city of New York has around that amount of individuals. I would have checked it beforehand. So yeah, that is an accurate value. Right? Now, let's say we want to go smaller. We don't want to know the entire New York City. We want to know about Manhattan. What about the amount of people that are living in Manhattan? So that is what this third query does for us here. Yeah, that is what this third query does for us here, right? It filters the total population where the borough name is Manhattan. So there are two queries or two functions being applied here, the sum and the where function here. All right. So this allows us to streamline these demographical studies or these citywide analysis whenever we're doing it. And right, execute. Now the borough of Manhattan has that is 1,585,873 individuals. Right? And obviously, if Manhattan is found within the city of New York, it will have a smaller value than the total value for New York City. All right. We can also use um, the queries here to do more advanced mathematical calculations. In this case, we're calculating the percentage of an ethnic population, and we're also grouping it by borough. So again, two functions we're using here. So we use the group by function to aggregate them into those different categories into those different borough names. And we looked at those earlier. And then we are calculating a percentage. So we're multiplying the total population of, in this case, the white, right, by 100, and then dividing that by the overall population of New York City. And let's see what we have here. All right. So as you're seeing here, of the boroughs in New York Cities, of which there are five, Queens, Brooklyn, the Bronx, Manhattan, Staten Island, of those boroughs, we now know how many individuals with white ethnic or that are considered white are found in percentage are found throughout those boroughs. So we see here Staten Island has the largest being 72.9%, whereas the Bronx has the smallest 27.9%. So again, I hope you're thinking forward that the uses of these types of calculations, of these types of scenarios, right? So this is valuable work, right, that has been done very quickly. If you want to do some, again, demographic studies or some policy planning, all right, this allows you to streamline the analysis for those stuff, all right? And we have another one here, whereas we're measuring land areas, so we're able to measure geometries as well, all right, for specific features that are identified in the database. And in this case, we're pulling the borough of Manhattan, and we're calculating the area, ST area of the geometry, right, which measures the geometric area of that borough. All right. And again, these queries like, whoops, get that back. Oh, so what you're seeing here, right, is just, it's just the area um, for the different neighborhoods in Manhattan. So we don't, what we don't have here is the names of those neighborhoods. So, I mean, this itself, it's a bit meaningless, but you know the values if you're looking for the highest, lowest, you can get that, but it doesn't mean a lot without the name of the neighborhood present, and it's not in any order, it's just random as well. So, again, you can quickly modify this to, add in the name function. So we're gonna select that will be we're selecting neighborhoods. Yes, we're gonna select the neighborhoods and the name of the neighborhoods, and we want to find their area. Yes, so what we're seeing here now are the names of the neighborhoods in Manhattan. And if you remember earlier, there should be 28. Yes, there is 28 neighborhoods. Right? And the other field here shows us the area in that would be meters square meters of those neighborhoods. But again, they're not in any order. And if they're not in any order, again, you can make modifications to the query to give it some sort of order in it. So I think we're gonna so to do that, we're just gonna I think it's order um, by area. Let's go with descending. Yes. There's something else. Yes, we have to add in. We have to define what the area is. Area. Oh, so yeah. So you have to be very careful when you're typing these things because something else is missing. Order by area. Am I missing something here? Line 5, it's saying. That should not be it. It should be running. Oh, unless that is my yes. Yeah, so as you're seeing here, mm, yeah. So as you're seeing, right, small errors within the query can make it result can make it not work. So you have to look out for those tiny stuff. But if you're somebody who has experience in these type of stuff, maybe not necessarily for geospatial stuff, but still in general, I mean, it is something that will not be much of a problem for you. For the rest of us, you have to look, be a bit more careful when you're inputting these characters. Yes, so what we're seeing here is now the neighborhoods in the borough of Manhattan, their area in meter square, and they have been sorted in descending order. So this here means Washington Heights has the largest area and Little Italy has the smallest. Right? Good. So moving on, well, let's take a bit of a breather right now and do some trivia because I mean, I've been talking. Let me have you thinking for a moment right now. So, upon researching and compiling this tutorial, uh, I said this results when you add the PostGIS. It's essentially a GIS platform when it's all said and done, and that got me thinking, what was the first GIS? system? What was the first GIS platform? And I honestly thought it was the Esri systems that were developed by Jack Dangermond and co. But apparently, it's not the Esri stuff that he developed. It is actually the Canada Geographic Information System, right? That is what most people consider, sorry, to be the first uh, GIS platform, and it was developed in the 1960s, um, obviously in Canada, right? So that is actually a good piece of knowledge for you to know. Maybe it's gonna pop up somewhere. Maybe it's gonna be a useful piece of information sometime down the line, or maybe it's something you already know. Either way, it's still a bit of fun of knowledge for us to know. And another question I think as GIS professionals we get asked a lot is, what is your preferred GIS platform? Huh? Do you have a preferred GIS platform? If you do, you can sure to leave it in the comments below. And if you also want, you can say why it is a preferred, it is your preferred platform. But for me personally, uh, it depends on the objective of the study I'm doing or of the work I'm doing. Right? That and the nature of the data set I have, that will primarily influence which of the platforms I choose to do my work on. Right? Because I mean, most of us have knowledge in the ARC, GIS platform, the Esri stuff. Most institutions, I guess, use that. Some use the more open source stuff like QGIS, uh, like the Postgres as well. Others, I don't know of any organizations that use the Earth Imagine, but it is something I've used as well. Other people are more familiar with the cloud computing, the GE stuff, and even to some extent Arc Online. I mean, there are a lot of popular systems out there, but then there are some lesser known ones as well that do very good work as well. But again, it all depends on what is, I guess, what suits you to some extent. But don't ever let that stop you from opening your sites to, learning a new system, a new platform to do the work. Because who knows, you might find a platform that is actually, dare I say, better or more efficient actually than what you're presently using. All right. So don't forget to leave that comment and let us continue. All right. So we're now moving on to what are spatial joint spatial relationships. So in our geospatial databases, spatial relationships describe how different geometries, we mentioned the points, the lines, the polygons, how they interact with one another. Right? And there are some common spatial relationships that everybody knows, and there's some more uncommon ones. So there's containment, which is when one geometry completely envelopes another. Let's say a neighborhood containing a park. There's intersection. That's when two geometries share some common space, like a river crossing a city boundary, two roads crossing, two rivers crossing, things like that. There's adjacency or touching, which are when geometries share a boundary or a side, but they don't overlap. They're just sharing that boundary. Uh, there's proximity, which is when geometries lie within uh, some sort of specified distance from one another, right? So it's something like containment, but it is a more restrictive aspect of containment, if you will, right? So in all spatial joins, they leverage these relationships and combine records from two different tables. We've looked at those tables I had earlier shown you, right? So these spatial joins, they combine the records from two different tables, right? But it is based on their spatial relationship, right? So you might want to join a table of, let's say, accident data, where actually accidents would have occurred, with a table of city district polygons. right? And you want to determine in which district did each accident occur in, right? And spatial joins, they operate much like the traditional SQL joins. However, again, they use that spatial function, right? And that is the key for linking the data rather than some discrete attribute matching, right? Now, why are spatial joins, spatial relationships helpful? So they are invaluable because they allow us analysts and GIS professionals to integrate multiple data sets based on location rather than just some common attribute key. And these capabilities, right, allows for the uncovering of patterns because by joining data and spatial relationships, you can expose hidden patterns. Clustering of events within a specific area is one of them, which might not be visible when the data are viewed independently. All right? It enhances analysis. Yes, whether you're aggregating demographic data with, let's say, within an urban district or connecting environmental data with a geographical feature, the spatial join make it possible to conduct more complex analysis directly within the database. Right? And then lastly, we have here is that it optimizes performance. Right? So when you have these spatial indexes, right? It allows for more efficient, it allows for functions to execute more efficiently, right? And extensions like PostGIS, does this. Well, maybe in another video we'll go over spatial indexes, right, and see how they help us be more efficient in in reaching the results from queries that are over large spaces or over large data sets, right? In terms of scale, geographical scale, right, and um, file scale as well, right? So it makes real-time analysis, right, more feasible, more time-friendly, right, and more optimized in general. Right? So in essence, these spatial relationships, right, and the joins that are based upon them, they empower users. I'm not going to say GIS analysts or GIS professionals. They empower any user to blend diverse data sources into something that's coherent to a spatial narrative. Right? And that is a cornerstone of modern GIS analysis. Right? Having a spatial narrative to the data you have, to the results that you are producing. So let's see some use cases, some examples, some applications of spatial relationships, spatial joins in SQL using the PostGIS extension. Firstly, we have here is that we can find say a population near a subway station. In our case here, we're joining two tables, the New York census block, right, and the New York subway station. So the census block contains population data and the spatial information on those blocks, and the subway station contains the geographic location of the subway stations. So the within function checks to see if a census block, in this case, falls within 50 meter radius of any subway station. And then it aggregates, look here, it aggregates the total population of those census blocks, revealing how many people live near the subway station. So if we copy, did I copy? Yes. So what we're seeing here in New York City, some 637,845 individuals live or live in a census block that is within a 50-meter radius of a subway station. All right. Now, moving forward, let's say we want to find neighborhoods that intersect a specific point. Let's say your realtor sends you a location um, of uh, let's say this listing that they have, and you want to know which neighborhood it's located in. These types of queries allows for that. Whereas we're querying, you see here, New York neighborhoods to find the neighborhood that overlaps that given point. The geometry from text checks, sorry, converts the coordinates, and this here is the reference system. It converts that into a geometry object, the text into a geometry object, and the intersect helps to check if that neighborhood is is within is intersecting with this point, and it will select which one of them intersects with that point. I think I yeah, my bad there on that. Good. Moving forward. Ah, I copied the same stuff. Good. And we're seeing here this point is found in the neighborhood of Central Park. And Central Park is in the borough of Manhattan. So I can tell you that when I would have selected these coordinates, I would have selected something at the center of Central Park. So I mean, you're seeing validation here. And in some cases, some people are reluctant to accept it because there's no visual well, they're not seeing a visual at this point. They're not seeing a visual representation of the data, so they might be a bit skeptical to say, on accepting it. But if you, and not everyone needs this, but if you require some boost in confidence, you can query something that something that is known, and it will obviously provide the right answer to that, provided the data set meets the quality standards and was inputted correctly and all of that. It will provide the right answer. And if you need that boost in confidence, you can do that. But for other people who don't need it and are confident with what they're doing, kudos to you, and keep moving forward on that. Also, we can find in this case uh, closest the closest street to a point. So let me just copy it here one time and let's go over. Yeah. Yeah. So what we're seeing here is we're selecting the name of a street, right? That and this function here, the right, this function here is a distance-based sorting operator. And it computes the shortest distance between, in this case, the street, the street and the point. All right. And we already went through this here order by, we're ordering in this case by distance. All right. And we're limiting the results to 5 here. And let's see. Yes, we do have 5. Now, that is telling us that the closest streets to this point in Central Park, the 5 closest streets to this point in Central Park are shown here. So the closest is the 85th um, St. Transverse Street at 77.3 meters. The furthest is 85th St. Transverse Street at 256 meters. So what I'm guessing here is that this street actually may curve around this location in the Central Park. So it is both the shortest and the furthest street, depending on which direction you end up walking, right? But again, it depends on the general geography of the location, right? So we're seeing here that that this can be used to identify um, features. In this case, we're looking at the nearest features to a specific point. I mean, there are a lot of use case scenarios for such a function. Moving on. Oh, we didn't do. I must have missed this one. This one here allows us to find streets that are within 100 meters of a point. All right. So it's the same point in Central Park we're looking at. And if we look back here, there's only one street that is less than 100 meters. So again, a good chance to validate our results. Again, we're selecting the name of the New York City streets that are within 100 meters of this point. Run. And that is correct. Only one street was less than 100 meters um, from the point, and that was at 85th St. Transverse Street. Right? So, I mean, we're seeing results here that follows with what we're doing. It's not we're seeing a result here and then a contradictory one next. Right? These it is based uh, with data, right? With the data that we input. The only errors that will occur are if there are errors in the queries or if there are errors in the tables themselves when you would have created or inputted or uploaded the tables into the database. We have some more here. So we want to find subway stations in Central Park, in the Central Park neighborhood. All right. So what we're seeing here, we're using the contain function, and it is checking. Where is it? It's checking to see if if the geometries fully contain each other. In this case, it is checking if New York City neighborhoods, right? The Central Park neighborhood contains any subway stations. And to do that, again, it is joining these two tables into one using, again, that geospatial aspect that is provided with the data. And are there any subway stations in Central Park? Yes, there are. Oh, I forgot. I didn't mention this. But we're also selecting the routes of those subway stations. So there are 6 subway stations uh, in in this neighborhood of Central Park. There's a second 72nd, 81st, 86, 10, 103rd, 96th, and 110th. And we're seeing here the routes that those subway stations take you to. All right. So I mean, this is an uh, important result here. It tells you, are there any subway stations around me in this neighborhood that I'm going to live in that I want to, spend some time in? If I miss the bus, is there a subway station that I can go to? And where does that subway station take me? You know, all of that. Very important stuff. Moving on, we can again find the population, in this case, of Central Park, right? So we did this before, but that was in terms of a census blocks and that a census block and the entire New York and all of that. So those are more simple because you're aggregating over everything. But uh, this one is more specific because it is looking at different tables, right? Again, that is where the relationships, the spatial relationships come in. So what we're seeing here, we're joining the New York census to the New York neighborhoods table, and we are selecting the total population. We're aggregating it here, selecting the total population of of neighborhoods or of the neighborhood that is named Central Park. We're selecting all the census blocks within this neighborhood of Central Park, and then we are summing the total population of this neighborhood using data from another table, the census block table. Good. And what we're seeing here is that in Central Park, there are 46,600 individuals, with reference to when the census was taken. Moving on, we can then calculate distance here again uh, between 2 points. Now, given this is not necessarily, are actually the last two here, they're not necessarily spatial relationships um, explicitly. They're more geographical based queries that are possible um, with the PostGIS extension. But I mean, I added them because, why not see all you can see, know all you can know about the possibilities of this platform. So let's say for some reason you are again you're in Central Park and you want to get to another point. Uh so the other point when I was what did I do there? Yeah. So the other point I believe Yeah, the other point is in the Hamptons, which is at the upper end of New York there. So let's say well, we don't have any route data in terms of the road network, so we wouldn't know where to go. So we can't say, okay, that's going to be your driving distance or your train distance or your subway distance. So I guess the best thing we can use in this case, let's say you're in Central Park and your helicopter comes for you so you have your house has a helipad in the Hamptons. You want to know, okay, what distance am I going to fly? I know. And in this case, we do have a distance, and this again is in meters, and it is 100 and sorry, it's yes, 152,144 meters. All right. So what the ST distance function does is that it computes the geodesic distance as a straight line between Central Park and the Hamptons. Because like I said before, we don't know the routes that the train, the bus, the roads would take. So this is the best we can do with the data set we have at the moment. Right? So it looks at the first geometry, that is point one in the Central Park, and then the second geometry, point two in the Hamptons, and then it finds the distance between those two locations. Right? And I mean, in more complex scenarios where you do have routes available, you can use it, for travel, for mapping, and all those sort of stuff. And let's continue, with this scenario. Let's say you can find neighborhoods along the path over which you're helicoptering over. All right, let's say, okay, if I take this route, the shortest route, what neighborhoods would I be flying over? What would I be seeing below? All of that. Did I not copy? All right. All right. So we're selecting here again. You're looking at where where the line between these 2 points intersects with the neighborhoods, and we are looking here. Whoops, something is missing there. Let me see here. So again, you have to, whenever you're doing these types of queries, any coding in actual terms, whenever you're doing it, you must ensure, you have some sense of what you're doing, because if you're just typing randomly, you're gonna run into a lot of problem. All right, so you have to ensure, first of all, your variables are named correctly, your functions are correctly spelt, right? The format in which they are, it's correct as well. And then you have to look out for these things, the commas, the uplifted commas, the semicolons, and the brackets that, can really cause these errors. And sometimes they do take a while to find, which, gets it gets testing sometimes, to say the least. So let me go over this quick. Select name, borrow name. From New York neighborhoods, yes, where it intersects geometry, this geometry here, okay, from text point, this is here, this closes, this op, okay, so let me see, one, two, one, two, three, okay, so we're missing, you see here, we're missing, gonna be before, we're missing, uh, bracket. Yeah, we were missing a bracket. So again, back to our scenario, in your helicopter, what am I going to see when I look down? You are going to see at least seven different neighborhoods. Carnegie Hill, Central Park, obviously, because you're there. Upper East Side, College Point, Yorkville, Whitestone, and Steinway. Those are the neighborhoods you're going to see, and you'll be passing over at least two boroughs, that is Manhattan and Queens. All right, and to some extent you can even expand the search area in either direction to help you, if I look that over to my right or my left, what would I see there, what is only there. That is also possible uh, with the queries, once the queries are written correctly, that is. All right, so that is it for our practical applications. Yeah, that's it for practical applications. If you have any questions on these, I encourage you to either comment below or even do your own research, because I mean, there are a lot of documentation out there on how to do these things, and a lot of help provided by the community if you do need it. All right. So that is it here on, utilizing uh what are some use cases, sorry, of spatial relationships and spatial joins in Postgres using the PostGIS extension. So to conclude, we should understand that geospatial databases, they revolutionize the way we handle, query, analyze data that is tied to specific geographic locations. And again, unlike the conventional databases that deal primarily with numbers and text, these specialized systems, they harness spatial data types along dedicated indexing techniques, which is something I would have loved for us to look at, but maybe in the next video, like the R trees, and that allows us to ask more complex location-based questions. If you have a larger database, or if you're looking over a larger geographical area, the indexing really helps with that. All right. And then Postgres SQL, which we see here, is very robust. It's very flexible, as an open source relational system. And, as it becomes a fully fledged GIS platform with the addition of the PostGIS extension, it really is something else in that sense, because PostGIS enriches it by introducing the spatial data types and specialized functions, which empowers us users to perform more intricate spatial operations directly within SQL. And with these tools at hand, or geospatial queries, calculating neighborhood populations, determining percentage of demographic groups, evaluating how streets are related to some point. It becomes seamless when you're integrating it into data analysis. So by understanding the concepts like we looked at containment, intersection, proximity, we can join the disparate data sets based on their geographic interactions, right? And again, whether it is find that total population residing, at some distance from a subway station, like we looked at, or establishing which neighborhood overlap a given coordinate or a given line, right? These spatial functions, they drive insights that are simply aren't possible, with certain traditional attribute joints. So ultimately, by merging the power of the standard SQL with advanced spatial analysis, these modern geospatial databases, they uncover hidden patterns. They support decision making in urban planning, environmental monitoring, demographic studies. I mean, in basically any field that has geospatial data, right? And this integration of relational and spatial data, it paves the way for a more streamlined, efficient analysis and offers detailed narratives on the spatial world in which we live in, and it paves the way for more innovative future applications in GIS, right? So, if you are curious about, more advanced techniques like how, again, the spatial indices are structured, or how variables like projection, which is another important aspect, you should look at, like how the projection affects spatial analysis. It's something I encourage you to look deeper into. You can either look at the PostGIS documentation on this, or engage with the wider GIS community. We are a friendly bunch, right? I can leave my email below for you to contact me if you have any questions concerning the tutorial, or if you have a scenario of your own you want to ask. I'm available, or if you don't want to ask me, again, you go to the WiredGIS community, of which there are multiple forums available, and post your question right there. Maybe if you don't want to give specific details, you generalize it or change certain details. But we are a fun bunch, so I encourage you to do that. Again, please, if you have any comments, please add them below in the comment section. You can like the video as well if it was something you enjoyed. Um, and that is it for me. Thank you. Until next time, goodbye.